Okay guys, in this video we're going to be taking a look at a special property of equality that we use often when it comes to especially solving exponential equations. But since we're working with exponential graphs, it might be a little hard to see why I would want to do this in the first place. But it may be possible that I would want to know, say, where some exponential function, like this one right here, 2 to the x plus 2, comes out to have a value of 16. So at what x value would that happen? And so it is useful to use a particular property that we refer to as the one-to-one property of equality. And this is like one of my favorite properties. Before we even read the one-to-one property with respect to exponentials, the one-to-one property kind of says like this: if I had like ax plus b equal to ac plus b, then this could only be true if and only if x and c had to be exactly the same numbers here. And so the one-to-one property of equality, at least with respect to exponential things, says that for some base that is positive and not equal to 1, then b to the x equals b to the y if and only if their exponents are equal. And that might sound like a crazy thing, but if I said, I have 2 to the 5th equals 2 to the x, it's really just a property that says that, hey, x, it would only have to be 5 here. And going back again to why I might use this, usually it's not going to be written as 2 to the 5th initially. I might have something like some exponential function 2 to the x, and I want to know at what x value would 2 to the x have a y value of 32. And so it would be really convenient to recognize that, hey, 32 is also a power of 2. Could I rewrite 32 as 2 to the 5th and set it equal to 2 to the x, where both of these exponential expressions have the same bases, and so then we could just set their exponents equal to one another. So the one-to-one property of equality with exponential statements basically just says if b to the x equals b to the y, then only true if x equals y or their exponents are equal. So using the one-to-one property of equality, I want to solve all of these equations you see down here. And the thing that might be a wrench in the gears so far, or at least right off the bat, is this. We see that we have 16 to the power of 1 equals 2 to the power of x plus 2. Now my problem here is this. If I'm going to use the one-to-one property of equality, then that means that both sides of this equation have to be of the form something to the power of something, and they have to have the same bases. So in this instance, I have 16 to the power of 1 equals 2 to the power of x plus 2. My bases are not the same. And so our method here is going to be to rewrite both sides so that they have the same bases. And so I'm actually going to write that right here. We're going to rewrite both sides having the same basis. This is not always possible, but in several instances it is. And so I noticed that 16 is a power of 2, and so if that is the case, then I could rewrite 16 instead as 2 to the 4th, and I could not rewrite the right side, just leave the right side as it is. And so in this particular instance, you can see that 2 to the 4th is equal to 2 to the x plus 2. This is a pretty neat conclusion because this would be true if and only if 4 is equal to x plus 2, and we can just go ahead and set their exponents equal to each other. So what this leads us to essentially is that x equals 2, and maybe I should write it on this side just to stay consistent here. But if I was solving this equation, it'd be real easy to go plug this back in and check. I could say, 16 is equal to the 2 plus 2 power, or that 16 is equal to 2 to the 4th power, 16 equals 16, and so you could see that we get a solution here. So this property, we often use it in several instances where we have fractions. And so when you look at this next instance, I say, let's go solve for x. What can I take 1/3 to the power of to get 81? I'm not really sure. But if we could rewrite both sides of this equation as having the same bases, then we could maybe set their exponents equal to each other. So what do I notice? What is a common root that 1/3 and 81 both have? And it might be hard to tell at first, but they're actually both powers of 3. So in this case, I notice that 1/3, well, that's the same as 3 to the negative 1. So what I'm going to do is I'm going to rewrite the left side as 3 to the negative 1 is actually being the thing that's raised to the x here, is the thing that's being raised to the x. And on the right, I could write this as 81. Well, 81 is technically, it's 3 to the 4th power. If you're sitting there going, how am I supposed to know that? A little bit of guess and check goes a long way. But I put this 1 out in the front here just to as its exponent to put something in its place. But what I want you to see here is when you raise a power to a power, you have to multiply your exponents. So in this case, I get 3 to the negative 1 times x is negative x, And here I get 3 to the 4 times 1. I put the 1 out there just to go to show you that if it was something like this, you wouldn't have to worry about having this out here. But if you had 1/3 and you're rewriting it as a power of 3, you have to put that power of 3 on the inside, and any exponent that was already there stays on the outside. So if 3 to the negative x equals 3 to the 4, then negative x equals 4, and we get x equals negative 4. And again, we could go take 1/3 to the negative 4. That would be the same thing as 3 to the positive 4, which is 81. And so for this last instance here, again, we're seeing an instance where both sides are not written as a common base, but do they have a common root? So 81 and 1/3 had a common root in 3. 2 and 32, 32 is a power of 2 here. So maybe we rewrite 32 as a power of 2. So the left being already a power of 2 is just 2 to the x minus 2. But this case, I would say, what could I raise 2 to the power of to get 1 over 32? Well, I know that 2 to the 5th equals 32. So 2 to the negative 5 would have to be its reciprocal. And on the outside here, I won't have to put anything because it didn't really have any substance there to begin with. So 2 to the x minus 2 equals 2 to the negative 5, if and only if x minus 2, the exponent on the left, equals the exponent on the right. And as we add 2 to both sides here, we see that we get negative 3. And again, this would be really easy to check. If you put in 2 to the negative 3 minus 2 on the left here, what we end up with is 2 to the negative 5, which is the same thing as 1 over 2 to the positive 5, which is 1 over 32. So we get a solution here. So this one-to-one property of equality, we're going to use this a lot, but get used to just rewriting both sides as having the same basis so that we can equate their exponents. Cheers.